Namaskar. So in this video, we will discuss one more question in identity theorem. Okay, version 2. So you can see a domain is given. Certainly the given domain is open unit disk, right? The disk like this. And f from D to C is what? An analytic function which satisfies this condition. Okay, so yes, we are going to write this 1 by n is equals to z. Why we are going to do this? Certainly we will discuss. So hence you can see what 1 by n is equals to z. Then your n will be equals to what? 1 by z. So you will write your f as f of z is equals to 2 by z upon 3 by z plus 1. So finally you will write it as 2 by z upon 3 plus z divided by z. So we can say this is nothing but 2 by z. Okay, 2 by z into z by 3 plus z. So z to z will be cancelled and we will be able to see our f of z as 2 by 3 plus z. So this will be our f of z, right? This will be our f of z. Now what was identity theorem? Identity theorem version 2 was what? If you have f and g, two functions analytic on D, okay, D is connected, and if your f and g are equal to each other on A, and if A contains the limit point in D, I mean to say A dash intersection D is not equals to phi, then your f will be identically equals to g on D. I mean to say for all z, your f of z and g of z will be equals to each other on the domain D, isn't it? So hence you can see what you have f of z is equals to 2 by 3 plus z. Let me write over here, f of z is equals to 2 by 3 plus z. So if I will tell you that let's call it g of z to understand the identity theorem. So hence your f of z and g of z are equal on which set? Certainly you can say that set is nothing but 1 by n, n belongs to n. Why these two are equal, f and g are equal on this? Because you can easily see if in place of z, if you will put 1 by n, then it will become f of 1 by n. And in place of z, if you will put 1 by n, then you are going to get this again. So for z is equals to 1 by n, these two f and g are going to become equal with each other. Okay, so finally you will say what f and g both are equal to each other on D. Both are identical on the domain. Okay, so certainly this is the thing. So now we are able to accept this as our function on the domain D. We have obtained f of z is equals to 2 by 3 plus z as our function on D by identity theorem, isn't it? Why? Because your 1 by n will go to 0 and this belongs to the open disk D. So certainly A dash intersection D is not equals to phi. So by identity theorem, these two will be equals to each other for whole domain, isn't it? And that's why we will take f of z is equals to 2 by 3 plus z as our function for the domain D. So f of z is equals to 2 by 3 plus z. So in place of z, if you will put 0, then it will become 2 by 3. So f of 0 is equals to 2 by 3. If 3 plus z is given, so you will put what? Z plus 3. So z plus 3 is equals to 0. So z is equals to minus 3. But it is said that z is equals to minus 3 is a pole. But actually this is not a singularity for the given function, because the domain of the given function is a unit open disk and your point minus 3, z is equals to minus 3 is outside the domain. So it cannot be a singularity. It will not be the pole for our f of z is equals to 2 by 3 plus z. Many of a student has done the mistake over here in 2011. So z is equals to minus 3 is certainly there by putting denominator equals to 0, but z is equals to minus 3 does not lie in the given domain. Option C is not right because 3 does not belongs to our domain also. Okay, 3 does not belongs to your domain, then how shall you put this 3 as input? You cannot do it, right? And therefore you shall say option C is also wrong. And yes, such function exists, that's why option D is also wrong. So your final answer will be what? A only, isn't it? Here 3 is outside the domain, it cannot be taken as input, and here -3 cannot be the pole because -3 is also outside the domain, so you have to take care of the domain. Okay, we'll meet in the next video with maximum modulus principle problem. Okay, till then, take care, bye bye, thank you.